A couple of years ago into this project because we wanted to begin to look at soil fertility. Full season, well, as full as I think we can. We started in June. We actually took some soil samples in May, but we actually analyzed them beginning in June, and we stopped in mid-October. Okay, so we still have some soil samples to take in the project this season. Larry came in with his expertise as a soil scientist from NDSU, and he's been on the faculty for how many years? You don't want to say.
Almost 30.
Almost 30 years. Well, I got you beat by 10. I've been at this for almost 40 years.
Yeah, you're a little bit older than me, though.
No, I'm not much older than you. How old are you?
Huh?
How old are you?
I'm old enough to retire.
Well, so am I, some time ago.
Well, a little bit ago. You've probably been longer than I have.
Yeah. Well, I'm 70.
Oh, I'm still younger.
I know, I told you you were.
You got at least 3 years on me.
Anyway, enough joking. What we'd like to do is have you give us some thoughts that you've got on the work that we did in collecting these soil samples and kind of what you see. The one problem, I think, is when you get we got 1 year of this data. It's a tremendous set of data of soil fertility from the start of the season to the end of the season. And we'd like to repeat it. It's just an awful lot of work, I can tell you that. I'd rather stack square bales than do soil samples, but neither one of them.
I've done both, and they're both work.
Neither one of them are fun. Anyway, Larry, share with some thoughts with us.
Okay, thank you. I'm going to back up a little bit here, and I've got somewhere here, I've got a good-looking, almost cowgirl here. The only thing she's lacking is cowboy boots.
And a horse.
And a horse, but cowboy boots help. Okay, so I've got some graphs here that summarize the data from our work last year, and I know how much work Doug and his crew did in collecting these soil samples every couple of weeks. He's collected samples of all of these plots, and the reason we do that is because there's variability in soils out here, and so they really need to see what's going on during the season. Now these that I'm going to show you are a summary of the nitrogen levels in these soils across all crops. When we start looking at each crop, it goes every which way, and you know, it almost makes me pass out looking at all the busyness in there. But anyhow, Doug also has some native grassland sites to compare here. You've got, what, one in section 15, one in 16, and then one over here in 22.
Over there in 22 and south.
Or 22 over there, yeah, okay.
South and 19.
Yeah, on the south end here. So anyhow, what I'm showing here is 3 lines. This is the nitrate. Now normally in the soil test, what we do is we look at nitrate in a 2-foot profile. And these are the averages of the 2-foot profiles per date, by sampling date, across the season. The gray line here is the grassland average. This is the cropland average. Now, one other thing that Doug did, which is kind of interesting, is he and his crew put some exclusion rings out here. Basically, what they're 2-foot sections of 8-inch irrigation, but 8-inch irrigation pipe out here. And you've got, what, at least 3 in each block, in order to exclude the the roots, because the roots have a lot of effect on that, you know, what's going on in the soil, the processes in the soil. And it also affects the microbial systems in the soil. Roots are very leaky. And because they're leaky, they put stuff out which actually stimulates microbial growth. Okay? And it's basically, it could be sugars, it could be, a lot of them are organic acids, things like that. They're organic matter, and so it stimulates organisms so they really blossom, and they help turn over the organic matter in the soil and do other things. By excluding the roots, it gives us an opportunity to look at what happens without all that activity. The other thing is, if you got roots in there, they're taking up the nutrients. So by excluding the roots, we can see what's happening just naturally without any interference and what the crop effects in there. So as you can see, as we begin the season here, the grassland is pretty much a straight line. And the reason for that is that there's not much happening in a grassland. It's been there for a long time. It's pretty stable. It's reaching equilibrium. So the constant slow turnover, but there's nothing drastic going on. We're here, even though these are no-till, you still have that seeding, putting a new crop in, and so there's some other disturbances that are going on even just by that seeding situation. So generally, and this is pretty common, in the spring you start out at some level here. This is about 47 pounds, I think, of nitrogen as nitrate. Now, when we do a nitrogen salt test, we test the nitrate. These are all in a 2-foot profile, just like we would a normal salt test. Okay? So, anyhow, early part of the season, the crops get planted here, kind of level, and they start dropping off as the crops start growing. Okay? And then it kind of sort of levels off here. There's some fluctuation, and that might be due to weather. You get a dry period where you're not going to get much mineralization, because mineralization is going on all the time by those microorganisms which are releasing nitrogen out of the organic matter and plant residues and whatever else is out there to the plants. But when you put the exclusion rings in here, you can see that you had to wait until you could put them in here about early July. So from early July through the rest of the season, you see that with the witch not being there, there's a fair amount of nitrogen being generated just naturally. And there are microorganisms in that too, but they're just, they're just plugging along doing their thing, putting out nitrogen. We don't know if this drop off here, if you remember last fall, somewhere around in here, between August 11th and somewhere in September, there was about 10 inches of rain. Doug's busy. But there's a lot of rain in this area. And so we don't know if this is due to leaching or maybe denitrification, because last year when we were out here, there's water standing in some of these rings, which means it went anaerobic, so we might have just lost it by denitrification. But you can still see there's a big separation between the crop and the rings without the crop in them. Now the thing about looking at curves like this, it could be a little bit misleading because we don't capture everything that's going on here. What we're doing when we sample, we're sampling at a point in time. And so we don't know what happens from this point in time to the next point in time. What I'm thinking is there's probably a lot of cycling, nitrogen cycling through the system. And if we look at some of the other components of nitrogen, and I'll have you grab the next one, I'll take this one. We also looked at the ammonium. Normally we don't look at ammonium in a soil test because ammonium is very, very variable, and it can vary by temperature, by moisture, by season, a lot of different things. But when organic matter breaks down, the first thing that's released from the organic matter is nitrogen. And organic matter is the biggest reservoir of nitrogen in our soils, the natural reservoir. So what happens, most of the nitrogen in plant materials is in the proteins that are in the plant materials, crop residues, whatever is out there. And so what's happening, the first group of organisms that attack that organic matter is they start releasing ammonium. That's called a process of ammonification. Okay. Now the thing is, there's other organisms there that convert that to nitrate, and that's called nitrification. Okay, you probably heard these terms in some aspect or another. So the first thing releases ammonium. Now ammonium won't move in the soil, so it'll attach to the soil particles. It's positively charged. Soil particles tend to be negatively charged, so they stick to the soil particles. However, there's organisms there that do nothing but convert ammonium to nitrate. Actually, there are 2 steps in it, but there's a certain population. So if all of a sudden if there's a supply of ammonium out there, these populations start growing and start attacking that ammonium and doing the conversion bit. So there's a constant stream and constant turnover, constant cycling into the nitrate. So when we do a soil test, we look at the nitrate because that is sort of the end product. And we normally don't look at the ammonium, although I think there may be reasons we should look at it, but most people ignore it because it's hard to really pin down what's going on with it. And there's been a lot of people doing work on nitrogen for probably a century and a half. I mean, they've been really dealing with it since the late 1800s. And they always sort of ignore ammonium because it's hard to account for. It's hard to account. You don't know where it's at. We know it's there. We can run a total nitrogen. We know that that's the potential. There's a lot of nitrogen. Only about 3% of the nitrogen in the soil is actually plant available as ammonium or nitrate, or what we would call mineral N. But it's there, and it keeps on cycling and being produced. The thing is, which is interesting, that and I think sometimes a lot of us soil scientists miss something, is that plants can utilize that ammonium just as well as they can the nitrates. Especially grassy type plants, corn, wheat, they can take up the nitrogen as 50% ammonium, 50% nitrate. Except most of the time in agronomic practice we ignore the ammonium because we don't know how much is going to be there because it's going to turn over real quickly, become nitrate. And we're concerned about the nitrate because that can leach. Okay, so there's a lot of, when you're starting to deal with these systems, there's a lot of things you got to consider. But if you look at it early in the season, and this, again, the gray line is the grassland, and I'm not sure why we've got this bump right there, but it's probably got something to do with, you got a dry spell, and a lot of ammonium is being produced, and the organisms that are converting ammonium to nitrate are not as active, so you get an accumulation of ammonium. Okay, and again, remember, this is just a sample at a point in time, so between each sampling point, there's a lot of things going on. So anyhow, the cropland starts out a bit higher. Okay, again, we've got a pretty stable system in the grassland, so there's not going to be a lot of turnover. So the beginning of the season, it's cold. We may not have the nitrification process really going yet, so it starts out fairly high. Now look at that, that's over 100 pounds per acre. It is plant available, but we don't know if it's going to be there for the crop. Okay, so anyhow, early in the season, you get all of this being converted to nitrate, and that's where your nitrate's fairly high up there and it drops off. And then it starts, you get the season warming up, so you start, this speeds up again. But then by now the crops are growing, and so they're starting to take up a lot of nitrogen, so you start depleting that, You're tying it up, the crops tie it up. And at the end of the season, you're down to about 30 pounds per acre as ammonium. So again, we don't normally look at the ammonium because it can be very transient. It can convert pretty quickly to something else, mostly nitrate. Okay, so let's take the next one there. Let me take that one. And so what I've done is I've calculated out the total. This is ammonium plus nitrate at each point in time. And if you look at it, if you draw the line in the middle, that's 80 pounds. That's a lot of nitrogen that's plant available during the season. Even though at a point in time when we take a soil test, we're not seeing it there. So there's a lot of nitrogen. And again, like I said, we're sampling point in time, and we really don't know, what's going on out there, because it's really hard to follow this stuff. We can figure out what's happening at the beginning of a time period and what's at the end of the time period. And we can guess at what's in between. We know what's going on, but we don't know how much plant available in is at this date or this date or this date. But looking at this data, and what makes it so interesting is it tells me that there's a lot of nitrogen in that system, and you're not putting on much nitrogen. The recommendations aren't that high. And a lot of our recommendations for nitrogen have sort of in the background incorporated this without it consciously being incorporated. So it's kind of interesting, but this is basically a combination of the ammonium curves and the nitrate curves. And you see that this difference here is much narrower in the total than it is on the nitrate. And of course with the ammonium, it parallels the line of the crop. So it's really, you start thinking about this thing, there's a lot of dynamics in these systems. And this is where we've got some of the benefits of the cover crops, because if we've got all of this stuff going on, they have an opportunity to capture that and immobilize it. Okay? And if they mobilize it, then it's going to be in that residue or even the forage. And if we graze this stuff, we're running that, the cow's a combine. It's going in one end and coming out the other end, and it's being spread out back on the surface. So we're also spreading manure out there. Okay, now we can estimate what it is. We don't, run around with a shovel trying to measure how much a cow poops, you know, and how much they put out there, but we do know that it's enriched in nutrients. So within a system, you know, the dynamics are really interesting. And the big thing in any system we have, especially if you put cover crops out there, have stuff growing there, producing residue, you know, when we take off a corn crop, and if we take everything off, we're still leaving almost half the plant out there, which is new organic matter that's still left in the soil. You know, now over time, we may deplete the soil some because it's not getting the full load that we would just by harvesting just the grain. But, you know, there's still a lot of organic matter going back in that soil. Then we cover crops. Now, Doug had an interesting slide this morning, and it's in your book, I think the second page of your book, where that curve where the nitrate came down during the season for the triticale, or the barley pea, wasn't it, or triticale vetch?
Triticale hairy vetch.
Yeah, triticale hairy vetch. The hairy vetch produces nitrogen, but most legumes are also good nitrogen scavengers. They don't produce all of their nitrogen. They take so much from the soil. But it's being incorporated in that plant. Okay, so what you're getting early in the spring, you get a high level. As the crop starts growing, it depletes the nitrogen. Then you cut that off as hay. Okay, you stop the depletion because you kill the crop. So then you get this bump up because you've got mineralization. Now you're in the warm part of the season, it's probably moist, and so any organic matter that's there is going to be converted into nitrogen. Okay? Then you plant your cover crop. Well, if you look at the lag time between the low point and the high point, that's only one sampling date. That's 2-3 weeks. Well, then the cover crop starts growing and it starts depleting it again. So it takes up anything that's been mineralized and put it back into that crop. And so whether in a regular farming system, if you've got cover crops out there and just leave the residue there, you know, kill it, leave it there, or if you graze it off, you know, you're tying up that nitrogen. And in situations, especially if you've got high nitrogen, which this part of the world isn't much of a problem, and some places you do have a lot of nitrogen, it manages to mine that nitrogen and store it in a form that won't leach, won't influence groundwater. But it's, you know, green stuff like this, I'll tell you, once you kill that stuff and the microbes get to it, it's released fast because it's easy to release. It's a lot easier to release from green stuff than it is from dry stuff. So, you know, the dynamics are really, really interesting. Now, the other thing, I'll take this from you, is we did some calculations on, this is the average, excuse me, this is the average nitrogen across the season for all crops, and compared it to the organic matter in these plots. Okay, and so that's what you got here. Now it doesn't look, you know, if you look at the regression equation here, it's not very significant. But what it still tells us is that for each percent nitrogen, we end up, each percent organic matter, we end up with about 8 pounds of nitrogen on the average. Now that's sampling at points in time. That doesn't account for that cycling in there. And I'll tell you, if I could figure out how to capture all that cycling, I'd be famous. You know, because it's not that easy to do. So, in the organic matter, the more organic matter you have, the more nitrogen you've got available. I've worked a lot in with carbon sequestration, and a lot of it, originally the funding was to look at, you know, using crops or grass or whatever to take CO2 out of the air, you know, to store it in the soil to mitigate global warming. I'm not even sure that stuff is going on the way they say it is. But from a farmer's standpoint, the more organic matter you can get in your ground, the more productive your soil is going to be. And that's very important because that's dollars. And if you can maintain it and improve it, that's even better because your soils are going to become much more productive. And you're going to need less fertilizer. So, you know, these sorts of things are very important to consider also. And anytime you can keep stuff growing out there, even if you harvest the tops off, you're still putting organic matter back in the soil. And the more you keep putting back in the soil, the better you are over time. I'll stop there. Are there any questions? Everybody, get confused, everybody.
A couple of questions.
Yeah.
Kind of related maybe to what you're saying about the organic matter. With Erin's study, that second study I talked about, she showed an increase in aggregate stability.
Right.
Over 3 years on the grazed treatments, there was no increase in the ungrazed treatments. Could you tell us more about aggregate stability?
Yeah, aggregate stability is kind of interesting, and we hear these things that, you know, cover crops. Yeah, you can put that down. Unless you want to hold it up there for a while.
I did put it.
Cover crops, you know, are supposed to keep the soil, you know, tie the soil up so it doesn't blow away or wash away, prevent erosion, basically. And the reason we have erosion is because the aggregates break down. If you have any aggregates less than sand size, which is about 0.84 millimeters, and a millimeter is about like that, you know what sand grain size is, it's subject to wind erosion. And in this part of the world, wind erosion is probably just as important or maybe more important than water erosion. Because as one of your old bosses, Tom Conlon, said one time, and I remember his quote very clearly, in this part of the world, drought is a natural condition. Okay? Anybody ever remembering? Well, a lot of you probably still remember Tom. A few guys here that might be a little too young, but Tom was an interesting character. And I always thought there was a very, very profound piece of wisdom. Okay? So what the roots do here, there's a number of different things that help improve the aggregate stability. When we're talking about aggregate stability, we're talking about the ability of the aggregates to resist coming apart in water, especially with a little bit of abrasion, okay? Which is good for also water erosion. Because if you get good, strong aggregates that are hold together, your soil is not as likely to erode. But it also improves the aeration, it improves water infiltration. And so there's a lot of physical benefits that go along with the other benefits. Roots can penetrate easier, you know, there's a lot of different things. But there's several different ways that roots can be or the soils can be stabilized. Number one, if you got a cover crop out there, the roots are stabilizing the aggregates. They're, you know, intertwined and they're just holding them together. Sometimes you get take a clump of grass, pull it up, and try to shake the soil off the roots, and you got a clump of soil on the roots. Well, that's because the roots are holding everything together. They kind of got it, you know, they're intertwined and going through and all of this stuff, and so you can't get the soil off. That's holding them together. The second thing is that roots tend to be leaky. And a lot of the compounds tend to be sort of like glues. And so it glues and sticks the aggregates together, holds them together better. The third thing is, if you've got a lot of biological activity going on, the organisms themselves, like fungi, molds, man, they proliferate everything and they just hold everything in a big chunk. I'm working on some ethanol processor byproduct, some liquid stuff. And if you put it into a bottle and incubate it, all I get is a big growth of mold. And then I'm working with phosphorus, looking at the effects on phosphorus. And then I'm trying to extract it, and I can't get them extracted because all that mold's holding everything together in a big clump. There's a big clump in there. It doesn't want to come apart. So they also cement it, but they also secrete glues. There was a person at the ARS station in Mandan who's left now, a soil microbiologist by Christine Nichols. She had done some work on you've probably heard this in the popular press, glomalin, which is a glue. It's a microbial glue. And there are processes you can put a dye to it, it's a fluorescent dye, and look at it, and it's just green, you know, under a certain light wavelength. You know, there's a lot of stuff going on if you've got plants growing there. One of the best things that happen in this part of the world is people have gone away from crop fallow to continuous cropping. Okay? And most of the soils, and this happened because of the Farm Bill in 1985. Anybody remember that? You keep residue on your land, 30% residue, and all of that stuff. The only way you can do it is keep something on there. Either go to no-till, which has some other benefits. You save water because every time you till it, you're losing water. Roundup. You don't need a till. You can kill off all the weeds and spray them out. You know, there's a lot of technology and things that have happened that have converted this. This whole area, we did some carbon work back here in the West River country back in the early 90s. And I've gone through ag statistics, and there are some counties out there that 80% of the crop line was in crop fallow. How much land is in crop fallow today? Very little. And I've done some work on looking at soil test data through the lab over between 85 and 2000, and you know, we saw tremendous increases in soil organic matter just in soil tests because of the continuous cropping, the no-till, you know, residue management over that time period. I mean, we're talking about, you know, 15% increase in organic matter. Not, you know, from 0 to 15, but from whatever it was to at least 15% above that on the average. That's a lot of organic matter when you think about it. A lot of increase in productivity. Now, having a wet spell, even out here for the last 20 years, hasn't hurt either. When we go back to that condition of perpetual drought, we may have to do some other things, but I think there's enough things we can do with cover crops and managing residues and no-till that we can still do a fairly decent job of crop production out here. But again, you're improving the soil organic matter. Okay, you're improving the productivity, and you're not losing soil going somewhere that contains those nutrients and things that you need to grow that crop. Did that answer that?
Yeah, so aggregate stability is a good thing.
It's an excellent thing, yeah. It's a very good thing. I love it. Any other questions? Yeah.
I might not have I don't have my book out here, but on the slides this morning, was the cover crop the least residual nitrogen of the cropping
Yes.
system?
It was, and
Yeah.
Could you explain that?
7 pounds per acre.
Yeah, it had 7 pounds per acre, and part of that is because the crop took up everything that was free.
Okay, and then that was grazed, so
Yeah, and but then, you know, the next spring it'll come back, and I don't know what it will be, you know, the following, and a lot of it depends on the winter conditions too.
so you test again in the spring.
Yeah, and you're going to have some mineralization before spring, not much, but then early spring, and depends when you get out there to plant. If you plant, you know, in late March, you may not have a lot of accumulation. But if you plant in late April, you know, there's enough of a warm period there. Those microorganisms are kind of like people. They like conditions like we like. 70 degrees, you know, and about 60% humidity. They're just like we are. And so if you get a very dry spring, or very wet spring, cold spring, you may not get that accumulation. But they'll kick into gear as soon as the conditions get right. And if you've got any residue there, you got manure out there, even those roots out there, they'll start breaking down. And if you go into a fall like this, and it freezes off, it doesn't desiccate, freezes off, a lot of that plant material there is going to be a lot quicker to mineralize. You get a fully mature corn crop or wheat crop. Yeah, following that was 17 pounds of corn, 17 pounds for 80 bushel corn.
Okay.
For the corn, for that crop, we put 17 pounds of nitrogen.
Even though I tested low, it yielded real good.
Yeah.
Yeah, so then when we came back with a different soil test, not this one we did in our research, we took soil samples.
Again this spring.
NRCS takes them for us from Kildare. They go out here with their truck and take soil samples, and then we send those in for analysis, and then they come back with the recommendation for nitrogen for this 80 bushel or so corn crop. And it was 17 pounds of N. So
Right.
they are accounting for
The mineralizable.
mineralization that will take place.
And we've got some, and I've been involved a little bit with it. You know, I've worked on. There's a long-term no-till site that down in near Furman, North Dakota, southeast, where they've got a number of different cropping systems there. And so I got a student look at The residue, we sampled the residue in the spring at planting, harvested it, looked at carbon nitrogen ratios. We've also done it right after harvest in the fall. And by our calculations, based on the amount of nitrogen in the system and the amount of carbon in the system, that tells us we need about anywhere between 80 and 100 pounds of extra N. If we were going to mineralize all of that organic matter, we know we're not going to do that. But with some of these long-term systems, we really don't have a good feel for the cycling again. And I'd love to be able to go out there and put some different nitrogen rates on it and see if there is a credit we can take. Now, in the wheat recommendations for the state, and there's been work done at all the research centers, or it was data collected at all research centers on continuous wheat. If you have more than 5 years continuous wheat, continuous no-till, the recommendation is you can take a 50-pound nitrogen credit for that. And I believe we can do that also for other crops, but, is 50 pounds the right number? The wheat, there's a good data where they can actually get a nice curve on that. The other crops, a lot of times it's kind of tough because people rotate things. And so you've got, on the east is corn, soybeans, or corn, wheat, soybeans, or something like that. A lot of times it's hard to tease out, these little nuances that really could make a big difference economically.
If you was to eliminate top material, all the roots, we're just talking roots, how would the comparison for the mass of roots compare between wheat, sunflowers, corn, and cover crop?
Well, it's about equivalent.
They're about the same?
Yeah,
Okay.
as far as compared to the above ground mass.
But I mean, if you eliminate amongst the crops, the
Right.
comparison.
Now, if you got corn, has probably got the most mass, so it's going to have the most roots.
Okay.
Okay. Wheat's going to have less. Once you dry that down, there's not a lot of dry matter above ground.
But I mean below the ground.
Well, above
Yeah.
ground. I mean,
Okay.
if you've got 3 tons above ground, you got 3 tons below ground.
Okay.
Okay. If you got 5 tons above ground, you got 5 tons below
Okay,
ground. If you
that's
got
what
a
I
ton and a half above ground, you got 10 and a half below ground.
That's
Okay.
what I was wondering.
Yeah. So it's sort of proportional. It's not exact, but it's sort of a rule of thumb.
Okay. Didn't know that.
But I've worked on a site at Oaks where it's just under irrigated corn plots. This is a sandy soil, which is sort of a weird one. But this is part of a larger North Central Region project. This is after 5 years. We don't see a lot of difference in organic matter. We take 100%. We were taking 0, 33, 66, and 100% of the corn stalks off. We don't see in continuous corn, we don't see a lot of difference in organic matter. Okay. But I'll tell you, there's a heck of a lot of difference in some of the other stuff like wind erodibility, aggregate stability, and water infiltration. And on these soils, really sandy soils, where you can't keep enough water on the surface from it going down, it cut down the infiltration. 100% removal cuts down the infiltration of the no removal to a third. So 2/3 of the infiltration is gone because of that. Again, we're leaving the roots there, but it does have an impact.
Okay.
When we go into corn-soybean rotation, it's harder because you're removing only the corn, so soybeans don't put on so much residue, but it's not as concentrated as continuous corn. So if you got corn and soybeans, you've got only half the cycles of corn in there that you've removed, so it's not as dramatic. There are some differences, but it's not as dramatic. But the water infiltration, that amazed me. We were getting about, and if I can remember correctly, it was like 18 millimeters of water per minute. That's 1.8 centimeters. That's about 2/3 of an inch. On the no residue removal. We were down to about 6 or 8 where all the residue was removed.
It's all running off the hill. It's all running down the creek.
Yeah, so, well, it's running down somewhere, but everything else is standing on you know, it just wouldn't infiltrate where we didn't remove the residue. And there was a lot of difference in porosity too. Where we didn't remove residue, there's all kinds of earthworms in there. You know, after we got done, we take the soil core out. We just had irrigation, 6-inch irrigation pipe cut in sections. We buried it about a little over 4 inches below and about 8 inches above, and kept 4 inches of water in there. We pull that up, and there'd be 5 earthworms waving at you, where no residue was removed. We removed the residue, maybe 1. You know, that's because earthworms feed on residue. And they're surface feeders. They feed on it on the surface and pull it down. But they also, you know, you could see the earthworm holes in there. So, I mean, you know, the more plant material you got on surface, the more earthworms you're likely to have. We had a guy a number of years ago did a survey all across the state on different tillages and earthworms. No-till always had more earthworms than conventional till. But the reason for that was that in the conventional till, you kept wrecking that earthworm's house, and he didn't like to live there. That has a lot to do with it also. On the no-till, they were left alone. You know, they just won't hang around where your house gets wrecked. I mean, if every year you had a tornado and you had your house wrecked, you'd move, right? You would rebuild more than once. Any other questions? Well, good. I must have learned them something.
Well, Larry, thank you very much for your insight into what's going on here. Again, we'll probably have another program next year. Hope you follow us, and we'll have some more data. We'll stack more data on top. Things do change, and so we'll be able to report on some of those changes. Thing is, they don't change as fast as we like them, and you have needs for research faster than we can generate it. But
every season's the same as every other season, right?
no, it isn't. No, they're not the same. They're so dynamic, so changing constantly. There's nothing static about what's going on here. So, anyway, I know you have places to go and things to do. Some have to drive quite a ways. So, thank you for coming. Even though a small group, you're certainly very attentive and interested in what's going on. So, thank you for coming. And perhaps we'll see you next year.